Good morning, everyone. So today we will continue our lecture entitled, I think, mass transfers. Yeah, this chapter 2. So as you know that we will learn about the mass balance first, like how we calculate the mass before we go to the energy balance. So maybe I think that you learn also about the mass and energy balance in the senior high school, right? So for example, if you discuss about the mass, it's of course like the mass is conserved. So it means that mass in equal to the mass out for the steady state, but for the energy balance, like energy in equal to the energy out. So in this case, if you discuss about the steady state and unsteady state, it's just in vary with the time. So all of the mass and energy there should be conserved. So today we will discuss further about this. So how the conservation of mass. So like we discussed before about energy balance and also the mass balance, all of them they are conserved. So you can see that in here. Conserve, what is this? What the meaning of the conserve? Conserve, it means that the total inside the system, or the total, if you have that supposed to be here, I have one system. So you have in and out. So the number of mass in and out, they should be equal. So this is, we call it that it's conserved. So in this case, like when you discuss about the conserve, that no mass loss or no energy loss. So if you're supposed to be in, you have the 5 kilograms. So in out, also you have the 5 kilogram. So if you're supposed to be in out, you cannot divide 5 kilogram, the same like input, there is something mass loss. So for example, in here, we have the problem of studying the total mass of water. Yeah, so I just take one of beautiful picture here. This is the natural lake in the North Sumatra. So if you visit Indonesia, it's in the Sumatra, yeah, Sumatra Island, because we consist of the many parts of islands. So it's not only Bali. I believe that most of you know Bali, but very seldom people know about the other area. So in here we have the Lake Toba as the one example in the North Sumatra. So this is one of example. So if you saw that this total mass of water in the lake, so it should be like mass in equal to the mass out. So you got to imagine, like for example, I have a case in the rainy season. Yeah, so the water when it's in summer, the water will evaporate into to the sky, and then they will form the cloud, and in the end, like it's we have a rain. So in this case, like the total mass in of water will be equal to the mass out of water. So what's the relation with the engineering process in here? So if you're supposed to be, you have the process. So I say that in here, perhaps I draw one process. So in this system, it consists of not only the separator or the vessel. Perhaps you're not really well known about the unit yet, but don't worry, like in the unit operation later, you will discuss further about each of the function of the unit, like separator, like the vessel, tank, or pump. So in this case, like if you discuss about the system, it's whole of the process. So once you have the pump or distillation of the separator inside, so you should calculate like how much the total mass flow rate or the total flow rate in. So in here, you can use m dot. Yeah, so m dot, it's discussed about the mass flow rate. So remember that every time I wrote the dot here, it means that indicate about the flow rate. So somehow we use also the molar flow rate. So if you calculate the total mass in, yeah, and then in out, mass out, yeah, so also the n out in here, n in, it should be equal. So this is, we call it conserve. So how about the mass in and then molar flow rate if the rate of change is with the specify of dt? So dt in here, it represents about the time, like we discussed before, you have steady state. Steady state, it means there t is equal to be 0 or time invariant. And then the other is unsteady state. They are function of the time, and the other one, it's not equal to the function of time, or you can say that is time invariant. So to calculate rate of change of amount of water in the lake, it's equal to the rate at which water flows into. In, it means go inside. And then out, it means go outside. That's why in chapter 1, I remind all of you to sketch, because you should know which the stream in and then which the stream out. So when they go in, it means inlet, and out, it means outlet. So to determine the precise rate of the change of the amount of water in the lake, we can use the sum period of the time. For example, if you would like to calculate only the specific months, I just want to calculate the total mass in the September or perhaps in October. So you can decide like the time. So we can use the equation change in the amount of water in the lake during the month only in September. The same with the in, it's only in September. And then minus out in the months of September. So similar case, like if you study for the engineering case, you have perhaps the T in second, or T in hour, or perhaps we calculate for the months, for 1 month, or even for the year. So this is actually, it's based on the time. So in this case, if you would like to calculate, for example, like how much the total energy the plant, or let's say that your process in a year, how much the cost that you should consume in a year. So this is function of the time. That's why when we learn in the basically, or like the first time or in the undergrad, you mostly discuss about a steady state. It means that they are not function of the t, but further you will learn about unsteady states. In the power plant or in the plant process, like white plant process, yeah. So the process is unsteady state. So we almost never find the steady state. But if you ask me, like, is it in the steady state process is truly have in the real? Yes. The answer is yes. We can still find the steady state process in the real case. For example, if you have reactor, you have the time in and then time, let's say, we can say that reaction in and then reaction out with the specific of the flow rate, yeah. Because the reaction is quite fast. So you can assume that your process is steady state, or we say quasi steady state. Yeah. So it looks like process looks like steady state, but actually it's not, because the process is too fast. So you can consider that no time invariant in here. Then how if you have the system here? So for example, here you have here, this is the system, yeah. I write here the system. Remember, previous we talking about surrounding. Inside is system, and the black line here, this is boundary. So whatever inside the M2, M3, MK, or M1, this is, we call it system. So, and they are inside. So the mass flow rate into the system at the K. So K in here is just represents about the symbol. So here I wrote the K. Yeah, so here, yeah. So you saw that there is some small, this is K. So it means to generalize the sequence of the numbers. So you can go further, M4, M5, but we just say K and 3 points. So it will be M dot. Remember here, M dot. So it should be consistent. When you say dot, it means the flow rate. If you just write M, so it means the total mass. The same like N, the total mole. So the Mk is larger than 0. It means the flow into to the system. If your Mk is less than 0, it means is flow out to the systems. I think this is not difficult for you because like in senior high school, you learn. However, in the engineering case, we need to review a little bit about the Mk, so you will understand further about how to calculate the conservation mass and then conservation energy. Okay, so we can go to this example. This is it's happened actually in the tank, yeah, or you can say in vessel, of course. So you saw that this solid line I draw here. Okay. So this solid line, we call it control volume. So what's the control volume? Somehow in the textbook, you will find they will write C dot V dot. It means control volume. So what's the control volume? Control volume, it means which system that we would like to calculate it. For example, I have large vessel, yeah, or large pipe. I draw the pipe here. So you can see that this is perhaps they have the flow in and then you have the flow on. So currently control volume, I just take a few system here, like just a small system. So this system, we call it control volume. So these systems will help you to calculate as the representative of the whole system. It's impossible, for example, we have the reactor and you calculate for the whole of it's a really large size. So you just take just some small control volume to represent for the whole. So here we can say that mass in and then mass out. Try to indicate which one is in, which one is out. So how about in exam? For example, like should I write the M in and M out? It's better. Actually, it's clear. Even though we know that when we correct your exam that this is in and out, but it's better you write like M in, M out to indicate like which one is in, which one is out. The same later, like if you discuss about energy balance, also the same. For example, if I have energy balance here, du divided by dt, yeah. So here also I indicate H in minus H out. So it's because in here is enthalpy, so we can use the cap or we can use the underline like we discussed before. So it's better to write the in and out. So the same here for the mass, we have dmCV. CV it means control volume. So it means the total of the accumulation of the mass in the control volume divided by dt will be equal to the M in minus M out. So here is the M in. If you have steady state, can I just write steady state with SS? So I will define here so you will not confuse later. If I wrote SS, okay, SS it means steady state. So if you have the steady state case, so you have the dmCV, yeah, divided by dt equal to the M dot in minus M dot out. So here, so because you have steady state, you don't have time invariant or t is equal to be 0. In the end, you only have M in equal to the M out. Yeah. So this is for the special case or steady flow. So we wrote here d divided by dt equal to be 0. Okay, so then we can have some few example. If I have the 4 kilogram hydrogen plus 6 kilogram oxygen, so I plus, but they are actually is not similar compound. Yeah. So here just simple case actually. So in here you have the H2 and O2, and you wish that inside you have reaction. So you need to have reaction, of course, because in the H2 and O2, they definitely cannot become H2O without reaction. Yeah? So with the specific temperature, with the specific pressures, and you can deform the 10 kilogram for the water. But if you see here that 4 kilograms, 6 kilograms, they should be equal to the mass in, yeah, because if you assume that it's steady flow or steady state, it means the time invariant. So how about if the time is unsteady? Of course, you have the divided by dt. One example here, mass is constant even during the chemical reaction. So later, like when you calculate, for example, I have A and then plus B become C. Then later, your calculation or your total for the mass in is not equal with the mass out. So it means there is something in calculation. That's why mass balance is very important. So first, we have the similar case. In here, we have the control volume, similar like the previous one, yeah. So you have, but in here you have two flow. One is M1, the other for the M2. And if you check the mass flow rate, it's equal, like 4 kilogram per second. And then on out, they will form another mass flow rate with equal to the 8 kilogram per second, because M1 plus M2 is equal to the M3. Yeah, as you can see that from the M in here, if I take it out, you assume, yeah, need to assume in here, steady state case. So in here, you have the mass in equal to the mass out. So of course, M1 plus M2 dot equal to the M3. Okay, so here mass balance for steady flow process. So we have the special case for the incompressible flow. So recall again in the chapter 1, we discussed about compressible. So compressible only for the fluid that have a phase is like a gas phase. But for the liquid, they are incompressible flow. So for example, in here we have the conservation of mass relation. We can be simplified when the fluid is incompressible, like in the case is liquid phase. For example, here we have the sigma in for the total volume. Yeah, we have here the V is equal to the sigma out V dot. So if you see that, if we have supposed to be single stream for the incompressible flow, how are we going to calculate? Because here we have T, it's equal to V zero. It means they are invariant with the time. So you have the V out, V in equal to the V out. So it means that if you have the case, let's say in here we have some cases, yeah, for the engine. So here you have the V1 equal to the V2. V in here we have the V1, and this should be V1. Sorry, so you can markable. Okay, so here, so we have the V1, it should be equal to the V2. So in here you can take, or you can show that the 2 kilogram per second, and then V1 is 1.4 meter cubic per second, and then M2 you have 2 kilogram per second, and then the V2 you have 0.8 meter cubic per second, because here it's indicate about the volumes, yeah, inside this engine. So you can calculate, because here we have different volume. So here you see that 1.4 and then 0.8. So you may calculate for the V1 dot, it's equal to the V1 multiplied by A1. The other the same, V2 is multiplied by A1 if you assume that area is similar. If your area is not similar, you have V1 A1 equal to the V2 A2. So in this case, we have the A1 equal to the A2 equal with the A. So if you check here, if we try to expand the equations, yeah, V1, it's normally we have the meter cubic, and then in here you have suppose, okay, velocity, let's say meter square per second, and then in here you have the meter square. So here a meter square. So you can calculate how to divide this. If you check that the V1 here, you have the meter cubic per second. Yep. So here also meter cubic per second. So in here meter per second. So yes, meter per second. Yeah, for the velocity. So you will have totally is equal with the V1 dot. It's coming from V1 A1 equal to the V2 A2, or in this case, because it's equal for the area, they are not changed with the pipe, so you have the V1 A1 and then V2 A1. So this is how we calculate. So you can calculate the total of the volume flow rate in and equal with the out. And then how about the, if you have the M in here is any kinds of the conserved property. For example, if you have total mass, total energy, and total momentum. So you can calculate by the M, T plus delta T, it's equal to the mass that enter in the system across the boundaries between T and T plus delta T. Remember here, T plus delta T, it's indicate of the function of time. So the same, in the other minus amount of the system that the left system across in the boundaries between T and T plus delta T. So we can calculate for the rate change of the mass balance. So normally we can calculate like M divided by T. So you can do the integration between T and then here T plus delta T. So you have in here M in, yeah, the same, plus integral T to T plus delta T M out. And the same for the molar basis. If you have the molar basis, the N dot divided by dt equal to the integral T plus delta T. You have N in plus integral T to T plus delta T. Same here and out. This is if you have the change in the between of the T and T plus delta T. The same for the M in enter, and then for the out, it's for the left of the systems. So later you can solve, use the mass basis or the molar basis. It's no problem. Both are the same. Yeah, so you can try to expand the equations. The same for the total energy. If you have total energy, we have here du divided by dt, also the same, T plus delta T, you have H in. So here I use, for example, the cap, yeah, the cap, and then plus T plus delta T H out. So later you can expand, you have energy kinetic, potential, and so on. For the momentum is similar. So the principle is, the concept, they are same, conserved. So that's why here we wrote M, it means the conserved properties. So the energy is conserved and mass is also conserved. But how about entropy? I recall directly, like in chapter 1, we discussed about entropy. Entropy is not conserved. Yeah, so the concept is only mass and then the energy, but it's not for the entropy. So later in chapter 4, we will learn further about the entropy. So we have the mass and then the pure fluids. So in this case, we can write some specific equations about the mass enter, or you can see in here that we have the mass and the molar fluid. So for example here, if you have the textbook is better with you, so you have here T1, T2, so you have dm divided by dt. It's equal, so in here, yeah, of course, is function of the t. So let me try to find the, okay, you have dt, so, okay, and then equal to the sigma k, and then we have here k equal to 1, integral t1 to t2 with the m dot k. So in here, don't forget if they are function of the dt, so you can write both in the same way. So if you have the delta t, we can try to integral the left side here. So the left side, it should be equal with the right side. So for example here, we have t1 to t2, and then here dm divided by dt, and then we have here dt. It's equal to the integral m at t1, m at t2, and then dm equal to the m t2 minus m t1. So this one, it means that the change of the t1. So the same way, if you're supposed to be like the previous one for the mk, so the sigma, this is for the left side. How about the right side? So the right side, we can do for the integral t1. Okay, so here you have the mk. Yeah. So mk in here, because we use the mass for it, so we have the mk dt. So it's equal with the mass that enter in the K system. So you still remember that before we discussed general case. So you have the mk. So mk is in the K entry points. So we can calculate with the delta mk. So in this case, we can rewrite the first questions. Okay, it's become m t2 minus m t1, and then here is sigma for the k equal to 1, delta mk. So the k, it was the entry points, or you can rewrite the equations, the first from the integration become the second equations. So if you have the independent of the time, it means that you don't have the delta t, or is m equal to be 0 in this case. So this is, you can write for the equations, this one, if you're supposed to be steady state case, we can try to modify the first equations, it's become the third one. So for steady flow, so you have the m t2 minus m t1, so equal to the sigma k is k equal to 1, so mk, okay, delta t, this is for steady flow. So it's in equation 3. So I believe that for the molar, similar, we just replace the m in here with the n. So for example, if you would like to expand the molar basis, can I just write here? So here for the molar basis is similar case. So we can have the integral t1, t2, dn. Divided by dt equal to the sigma k equal to 1. So in here you have the k entry point t1, t2, and then you have nk dt. So this is for molar basis, yeah. Special molar basis, it's just replace the m with the n. Then how about if you would like to integral. I think this one it's a similar case, yeah, like the previous one. So we do the integral case for the dm and then for the dn, and the integral mass balance similar like the previous that I wrote. So we have the m T2 minus m T1. So in here is sigma k equal to 1 total until the k and delta and k. So this is from the integral mass balance. And then in the end, for the steady flows, we have the m T2 minus m T1 and then equal to the sigma k equal to 1. So we have the until k, and in here mk dot delta t. This is for steady flows. So if you have the mass balance with the time, so you will have the mass in and mass out because you have the T2 minus T1. So delta mk, but for steady flow, so we can rewrite the equation that total mass is constant, that is multiplied by delta t. So this equation we will use further to calculate the process in the process engineering, yeah, like sum the process in the plant. So you need to know like how about the mass in and the mass out, energy in and energy out. So in this, the way how we do the integration, it's similar. Then the table 2 to 1. So this is the mass conservation of equation. You have the mass basis and the other molar basis. So like the previous one, we discussed about the general equations. So we have the m dt, yeah, equal to the sigma mk dot. So in this case, this is the general equation for the mass, and this one is the for the molar basis. So if you have the closed systems, remember what's the definition of the closed system? Yesterday we discussed open system, you have the mass in, you have the energy in, and you have the mass out, energy out. The same for the closed system, you don't have the mass in, but you have the energy flows. So in this case, you don't have mass flow. That's why in here we write dm divided dt is equal to b0, or m is constant, no in and out. The same for the molar basis. So how about the difference from the mass balance? So general equation for the m2 minus m1 equal to the sigma k for the k equal to 1 delta mk. So here is the for the k system. So you can try to calculate for the n the same, and 2 minus n1 will be equal to the sigma k equal to 1 up to k delta nk. So how about the special case? I have the closed system. So we can rewrite easily from the previous one, the m divided dt. You can write m2 equal to the m1 or m2 equal to the m1. That's why in the previous chapter, I always remind sketch. And then you need to assume the system. It's in, or they are open system, or they are closed system, or adiabatic. So you can define, like for example, for closed, m2 equal to the m1, m2 equal to the m1. So it's directly just based on the assumptions. And then for the steady flows, m2 minus m1 equal to sigma k equal to 1 up to k, and k delta t, like we defined before. And the for molar basis, m2 minus m1 equal to the sigma k to k equal to 1 and k delta t. Remember here the flow rate, the same, molar flow rate, mass flow rate. And we have the notation somehow, if they write mi in here, so it means that m equal to the ti. Yeah, so it represents about the time, yeah, like in, out. Yeah, so you can see that the time in. So time in t equal to t1 or t equal to the t2. The same here, and I equal to the n multiplied by ti. So one example in here, we have the illustrations 2 to 1. So I believe like this is one example. If you would like to calculate for the difference from the mass balance, you have the tank volume. So the tank volume is equal to 25 meter cubic, contains that 1.5 multiplied by 10 power of 4 kilogram of water. So in this case, you can try to write, yeah. So you have the tank. I just write some specific tank. Okay. So here you have the tank, and then you have the some water. So you have the in. You can say here just write this is the in, and this is the out. So okay, just put some. Okay, so here you're out. So we have the volume of the tank. It's totally the 25 meter cubic. So here we would like to divide which one is in, which one is out. And then over a 2 period of the inlet to the tank delivers 2.0 multiple 10 power 3 kilograms. So in here is M1. Yeah, so you can see in here is M1. So you have 2 multiple 10 power 3. Okay, this is the kilogram, so you can write kilogram. And then 1.3 multiple 10 power of 10 power cubic or 10 power of 3 kilogram lift of the tank. So in here you have the outlet port. So outlet port, we can divide this one as the M2, yeah. So in here I just write M2. So you have minus. Remember, for the out, you can write for the minus. For 1.3 multiple 10 power cubic, and in here is kilogram for the lift. Then we have the total of the water. It's equal to the 50 kilogram of water lift the tank by the evaporation. So it means that you have in here is M3. Because in here the question asks about lift. Lift it means out. It's go out. If they write inlet, it means in. They go in. So here you have M3. So you should write in here negative 50 kilogram. So how you divide the much water is in the tank and in the end of the 2-day period. So we can write in here M. And T is equal to days. Right? So it's equal to the M1, you have plus M2, you have M3. So here you have the M1, it's equal to multiple 10 power cubic. So I just write here because the unit they are the same. So minus 1.3 multiple 10 power of 3 and minus 50 kilogram. So then you can write here, it's the result is equal to the 1.5065 multiple 10 power of 4, and here is kilogram. Okay. So you have the original for these systems that you have the 1.5 multiple 10 power of 4 kilogram of water. So you need to consider, of course, in the calculation that you not only have the 2 multiple 10 power of 3, but also you have 1.5. So you got to in here plus. Okay, here I just wrote here 1.5 multiple 10 power of 4. So this is also kilogram plus. Because we already have 1.5, so this is the total originally. And then you can plus 2 multiple 10 power of cubic minus 1.3 multiple 10 power of cubic and minus 50. So it's equal to 1.565 multiple 10 power of 4 kilogram. So if they write for the M naught is kilogram per scum. But in here, we just write for the M, so it means it's for kilogram. So it means the rate of how we use the difference form of the mass balance in the tanks for the 2 days. And the other, we have the rate of the change form. for the mass balance. So for example, here we have the storage tank is being used in a chemical plant. So here we have the some tank that you have in the chemical tank and plant to the down fluctuations in the flow of the to a downstream chemical reactor. So you have the storage tank, and then they will flow the storage tank into the reactor. So this flow they go to the, let's see, okay. So here you have the reactor in, and then we go on. Yeah. So here is reactor, and in here is tank. So once you have the exit flow from this tank will be keep constant. So the exit flow, it means you have for the M out equal to minus 1.5, because here you have the statement that they write 1.5 kilogram per second. So if the instantaneously flow into the tanks exceed this, so suppose if your in is exit your minus, so the level of the tank they will go up. So the level of the water they will go up. So then while if the instantaneous flow is less, the level in the tank will be dropped. So if you're supposed to be in is less than the out, of course the level of water they are dropped. So if the instantaneous of the flow in the storage tank it's equal to 1.2. So in this case, you have that the instant flow into the storage, they keep constant. Yeah, for here supposed to be M in, you have keep constant, it's equal to the 1.2 kilogram per second. So how the rate of change of the mass in the tank? So in this case, we can calculate the tank case should be constant, or it should be like stable or steady, because you would like to know that the rate of the change of the mass in the tank. So you got to specify some time. So we can write the specific equations if you would like to calculate for the time. For example, here, if I want to calculate, it depends on the time, you will have dm divided by dt equal to the sigma, in here k, and in here I just wrote in k. Yeah, so this is what I mentioned before about divided by dt, because it's depend, they ask about the rate of change of mass. So if the question asks about the rate of change of mass, it should be divided by dt. Either this is steady state or unsteady state, depend on your assumption later. So how we calculate? So here we write the equations. I will change the color. dm divided by dt equal to the minus 1.5 plus 1.2 kilogram per second. So please don't forget to write the unit every time you solve the thermodynamics or any engineering case, not only thermodynamics. Yeah? So minus 0.3. So here it was points. Okay. 0.3. So it means that at the moment you measure that the amount of the liquid in the tank, they will decrease around minus 0.3. So here, that's why when you solve the problem, you must write the positive or negative to indicate which one is in, which one is out. So from this case, you know that your tank is decreasing because here it's negative signs. So that's every time they will minus 0.3 kilogram per second, or it's around minus 300 gram per second. So remember, like if you would like to calculate for the rate of the change, it means that you need to know about the period of the time. So here, the change, I give the statement, the total mass over the period of the time. This is its always function of dt. So don't forget to try to mention about or divide by dt, or try to calculate divide by dt if they ask the question with the change of the mass in the tank. And we have the next, it was the gas, rate of the change form of the mass balance. This is also interesting, a similar case like the previous ones. So in this case, you have the gas is being removed from the high pressure storage tank through the device that removes 1% of the current contents of the tank each minute. So each minute you already guessed that it should be divided by dt. So if the tank initially contains 1000 moles of the gas, how much will remain at the end of the 20 minutes? So for example here, I have the high pressure storage tank. I can say just that cylinder, that cylinder. I believe that in your lab, or if you visit the laboratory in the chemical engineering, you will find a lot of cylinder gas that actually we use for the cylinder gas. So here, perhaps I draw the cylinder like this. So you can just, okay, just use the fob to indicate more easily. Okay, so here you have the fob. They will go on. So the gas being removed. So normally, if you are sitting there in the gas cylinder, the pressure is around 150 bars, so inside of the cylinder. So that's why in here, like we have the high pressure storage tank through the device. Through the device here, the device we can assume to be supposed to be like kind of the valve. So we just remove 1%. So in this case, it's we can use the rate of the change. So you have 1000 contains 1000 moles, so we can write dN divided by dt, yes, here. So it's equal to the, here, because I already write dt, so I just write here is equal to the n dot. So here the n itself, n dot, it's given in the problem. They say 1%, yeah? So 1%, it means minus 0.01 multiplied by n. Because in here, like they say, remove 1%. Remove, it means negative. 1%, 0.01. So this is your n out. So we can write or simplify this based on the mathematics. So we have d ln n, we can simplify this, divided by dt equal to minus 0.01. So you can rewrite n dot equal to minus 0.01 multiplied by n, or d ln n, like the natural d ln n divided by dt, and then equal to the minus 0.01. Then we can use or simplify this solution with the first order differential equation. So it's in ODE, we can simplify ln from the first equations. We can define become the second one, and t divided, and t is equal to b0. So in here, the final divided by the initial. So the similar, actually, you can calculate by the integral t equal to b0, t is equal to t. This is also able, but here, because we use the rate of change, and then they give you that how much remain after the 20 minutes, I think it's more easy use the natural log. So if you saw that in here, we can write equal to minus 0.01 t. So this is become the second the second equation, or you can rewrite nt, it's equal to the n, t is equal to b0 exponent minus 0.01 t. So in this case, if you would like to calculate the 20 minutes, it means you just replace the t is equal to 20 minutes. That's why we discussed before, it's more easier to calculate, because for the rate of the change for the mass balance, we can use like natural log divided by the differential d ln n divided by t is equal to minus 0.01, or you can try to simplify the equation like nt equal to the nt equal to the 0 exponent like minus 0.01 t. So in this case, t you can replace with the 20 minutes. And how much the result if you write for the 20 minutes? So n equal to the t equal to 20. So equal to the n t equal to the 0 exponent minus 0.01 multiplied by 20. So here we will have the at 100 8.7 mole. Sorry. Okay. So they have a little bit. Okay, it's okay. So at 180.7 mole. So this case it means that if you leave for the 20 minutes and then you have 1,000 mole per gas, 1% from the 1,000 mole of the gas, how much remain after 20 minutes? So your gas is only up to at 180.7 mole. So this is the answer. So for this question. So I think so far it's not difficult, yeah. Compared than the similar like as the previous concept. So how we calculate the mass. So another problem, this is interesting. We have the rate of the change from the mass balance. So we have the open cylinder tank. So when you have the open cylinder tank, it means that they are not closed system here. So let's say here that I have the cylinder. Okay, cylinder. So here I have the open of the cylinder. And then from this case, I have the base area is 1 meter square and then the height it was 10 meter. So this is equal to 10 meter. Then the rate of the at which the water of the tank to the leak. So they give you the leak rate meter cubic per second equal to 0.5 root of delta P. So delta P in here, it means that the pressure difference involved between the fluid. Yeah. So with the tank and then with the atmosphere. So please determine the amount of the water in the tank at any time. So in here, we need to try to calculate the amount of the water it's at time, or especially for the height, because here when you have the liquid, so it means that you have some leak. I just put some star here, some star, so you can have let's say, oh yeah, so this is the leak. So you have the leak on the bottom of the cell. So in here, like you have the level of the water, they will decreasing according to the liquid. So we can try to determine of the tank at any time. First, we can see that the liquid, first we can solve by the pressure. So the pressure in the tank, it will be equal to 180 m, yeah, bar plus rho h. So why is plus rho h? If you consider when the tank it was the have a leak, so there is the open up space. So the atmospheric pressure, they will push the pressure, push the flow rate, and they can go out from the tank. So in this case, like the rho itself, it was density of the water, and the h it was the height. So the height of the water above the leak. So if you supposed to be have 10 meter with the specific of the water height, water level, because of the leak rate, so they will change between of the, depend on the time. So we can write in here like delta P, it's equal to the 1.013 plus rho h minus the 1.013. So in here, why we minus the 1.013? Because delta P, it means that the pressure in the open up space and then in inside. So you can solve that the difference. This is equal to 180 m. So this is equal to the rho h only. So density and then the height. So we can try to calculate delta P equal to 10 power of cubic in here in the kilogram meter divided meter cubic multiplied by H. So H in here is in meter. So because the unit, in meter, multiplied by 9.8. So in here you can have the gravity meter second square multiple 1 Pascal meter second. So this is just for the conversion actually. So when you have the conversions of the Pascal or of the unit, because you want to divide delta P for the bar, we have the 1.013 bar, so we need to have the same conversions. So here we have 10 power 5, the same bar divided Pascal. So I believe that in unit operation you learn about how to try to learn about how to convert the units. So here you can see like you have the all of this. So you have the Pascal second. So you have with the second, you can neglect each other. So kilogram with the kilogram. So meter you have with the meter cubic, and then also you have the bar. So in here you have the bar only, and then Pascal. So you can neglect all of the units. So you have in here 0.09807 H bar. So H in here, because we don't know how much the H itself, so we will have the H. So since the height of the tank, they will changing over the time, so we can write for the mass balance. This is only for delta P. So what's the function of delta P? So this delta P later, we will calculate for the high level of for the pressures, like how much the difference between the open up space and then with the inside pressure. So for the mass change, we can calculate by the MT. MT in here equal to the rho multiplied by A multiplied by the height multiple, this is depend on the time. So we have the rho, it means density of the water, because inside of the tank it was the water. So here you have the same like this one, 10 power cubic kilogram per meter cubic multiplied by the 1 meter square, because in the problem give you the area of the tank, and then multiplied by the H. Sorry. Okay. And then H multiplied by T. So in this case, we can write the calculation 10 power cubic and then HT, this one in kilogram unit. So the previous is in the bar, and then in here, because the mass, then it's in the kilogram. Then we can define how about the contents of the tank at any time. So content of the tank at any time. Content, it means the water, So the water at any time, we can try to solve the problem by the rate of the change. So first we can write the water at any time. So we can write the MT divided by dt. This is equal to the 10 power of cubic dHT. Divided by dt. So this is equal to, why in here is divided by dt? Because here is equal to the m naught. So m naught, it means that the mass flow rate. So we can try to calculate 0.5. So here, because the problem say in the previous, if we come back, they give you the specific equations, 0.5 multiplied by root of the delta P. So we need to multiply 0.5 multiplied by delta P. So delta P we know from the previous year, 0.098 around. So we can try to calculate by the minus 0.5, the root 0.098 HT. So here 0.7 HT. Okay, so here 0 with the 7. So then here is equal to minus 0.15 1.566, and then here root h t. So this is our mass flow rate. So currently, like if they ask you the questions about how the level or how high, how the level of the tank, if you're supposed to be have a liquid in the bottom, so of course like the level of the high also change, yeah. So from here we got the 10 power of cubic ht. So they are actually linear relationship with the empty. So we can try to figure out like, so we have the root ht in here. So we can directly write 2 root ht minus, this is at the initial, the final points, and then actually this is integration from the ht. So you can try by the integration for the ht, because we have the root h multiplied by t power of 1 divided 2. Yeah, this term you can try to integral, and then you will get the 2 multiplied by ht, and then minus 2 h0. Perhaps you ask me like, why we need to integral, teacher? Because we want to calculate the ht depend on the time. So you have the t1 and then the t2. So it means that when you integral ht with the integral t1 to t2, so you'll divide 2 root of the ht minus 2 root h0. So here we can divide 2 integral like a root ht will minus of the 2 ht. It's equal to the 5 at initial conditions, because in the problem say that you have the contains 5 meter cubic of the water, and then you have the level of the height, it's equal to the 10 meters. So in the initial, when the h equal to be 0, so it's equal to the 5. So once you calculate this, you have 2 root 5. So we can start minus 0.0, or I just write in the behind, in the beside, so it's more clear. It's equal to here 0.0 minus 0. Oh, sorry. Okay, I just continue here. 2, I write again for 2 ht minus 2 root h0, yeah, like we discussed before. And then you have here 2 root ht, right? So minus 2 root 5. So in this case, you already have this value before. It's equal to the minus 0.1566 multiplied by 10 power of negative 3t. So this you get from the calculations of the previously divides, and then we have the ht, root of the ht. We can try to expand. This is minus 5, yeah, from here, minus 0.1566 divided by 2 multiple 10 negative 3t. Then we can write, simplify, ht is equal to root 5 minus 0.7829 multiple 10 negative 4. This is t power of 2. So the mt, because the mt before, if you still remember, it's equal to 10 power of cubic ht, yeah, this is in kilogram. So we just substitute ht with this value. So 10 power of cubic multiple by root 5 minus 0.7829 multiple 10 power negative 4, and then here t power of 2. So it's equal to the total mass at each time. So this is normally if you supposed to be, you would like to calculate 1 hour, so it's equal to the 28,580 kilograms. So right, 580 kilograms. So this is P is equal to the 1 hour. 1 second, sorry. 1 hour or it's right, it's more clear. This is, it's if you completely drains, it's for the second, yeah, or in the 7.938 hours. So this is if you have the completely drained for the time. If you calculate for the time from here, so the completely mass you can get in the for the 7.938 hour. So if you would like to calculate for 1 hour, so you can it's around 28,900 for the kilogram. So in this case, like we can double check, calculate the T or calculate the M total for the tank. So it's possible. Then what's the command that we can use in here? Like actually, if you're supposed to be saw that the previous we calculate, we can see at in here that this one it's discussed about hydrostatic pressures. So the hydrostatic pressures indicate that you have the, I believe that you learned in the senior high schools about the hydraulic pressures, because your column or your cylinder is leak, so they will have some pressure from the atmosphere, and then they push the pressure inside of the system, and the flow is can go out. So this is depend on the high, and then depend on the depend on the pressures also, and depend on the total mass and with the time. So you can calculate, if you want to calculate, supposed to be like the total drains. Yeah, like the one that we calculate, this one. This is for the total time. If you want to calculate the total time, you just need to know about the T, like how much actually, like how long that your water we don't even like you put inside anymore, and then how long that it takes about the drain, like completely like all of the water go out. So you can use the T, or you can calculate for the M. Yeah, the M you can substitute like for 1 hour or some second, and then you can calculate for the total mass time. So that's true. You can calculate from these mass change equations. And we have the mass balance equations for the A multi-component system and the chemical reaction. So this is interesting because in the process we not only discuss about the total mass, but also we discuss about the chemical reaction. For example, we have the chemical reaction occur, so you have the mass and the mole balance, which is more complicated because you need to consider about the reaction. So before, if you don't have the reactions, you don't need to like consider about the reaction in the system. But here right now, if you have the reaction, so you got to consider about the number of mole. They can be increased or decreased. And then for example here, I have the molar, yeah? So molar in here, you have the dNi divided by the T. For example, this is the total molar change. And then you have the sigma, K is entry point up to K. So we have in here Ni K, so here is dot because it's rate of change, and then here you have the dNi divided by dt reactions. So this term is a new because you have the reaction, so you need to consider about this. And if you have the difference from the equation obtained by integrating the period, so if you have the T, for example, so you will have Ni T2 minus Ni T1. So then we can try to integral K equal to 1 up to K, and then here you have the T1 to T2 and K. So we can write NiK dt plus delta Ni reaction. Yes, this is equal to the sigma K equal to 1 up to K, and then here delta NK plus Ni reaction. Okay, so here it's the complete if you try to integral over the time. So you can assume that NiK in here, actually if you're supposed to have the steady flow, and then it's equal to delta NK delta T. So for the steady flow, we can write here, if you have the steady flow, yeah, just write on the top. So for the steady flow, we can have the delta Ni K is equal to the Ni here with the K multiple delta T. Similar, right? If you check with the mass, the same delta Ni is equal to the Mi. So here it's equal Mi delta T. So right now, if you have the chemical reaction, so because in this case we have many kinds of the chemical reaction, I give you one example. So in here we have the some mass balance. Let's say ethylene C2H4 and plus chlorine. Yeah, perhaps you know what is chlorine, and it's become 1,2-dichloroethane or ethylene dichloride. So here we have the C2H4Cl2. So this is ethylene, this is chlorine, and this is become 1.2 dichloroethane. So how are you going to try to calculate for the mass balance for this species? So we can try to use the species each one by one. So you got to divide each of them, each of the component. For example, C2H4. Yeah, how the mass balance for C2H4. So it means that we have D, and in here we can use the mass balance or molar balance. Here I think like it's much better use the mole, yeah, because in the chemical reaction we seldom use the mass. So I suggest we just use the mole balances. So we can, it means that I will change into N. So here Dn C2H4 divided by dt. Okay. Sorry, my written is not clear, but if you want to have the further discussion, it's okay too. For example, like also I try to see your record, but it's not really clear. Then please feel free to come to my office. So my office is 24 hours open for you. So you can try to ask from my record if it's not clear, it's no problem. C2H4, and then you have the, here I just try to define the one of the system. I think it's more easier for you. We can try to make the easy system here. So suppose because I have in here is C2H4, yeah. So I give this one 1, and this is the symbol, it's 2, and this is for the 3 because we have the 2 streamlined together. So I just give the symbol, it's more easy for you. So here is for the 1, stream 1, stream 2, and then become stream 3. So the final, because here you have the reaction C2H4, of course in the outside it will have the some C2H4 left. So we cannot like totally supposed to be, we hope that the reaction you don't have the C2H4 like totally is done, like conversion is 100%. So is most of the reaction you will have the C2H4 also in outlet. So for example, we have this case, yeah. So this one, don't forget like the previous we discussed about the molar exchange for the reaction. So you will have D and C2H4 divided by dt. So this is you cannot neglect because you have the reaction system. So it means that you need to consider also about this one. Then the same way in here, like if you check for the Cl2, same way. So for the Cl2 also we use the Cl2 divided by dt. Yeah. So in here I have the n dot for Cl2, but don't use 1 because 1 is there for the ethylene. So we have string 2 in this case plus the n Cl2 3 plus the reaction for the Cl2 divided by dt Rxn. Similar. Then how about the C2H4 or 1,2-dichloroethane? Okay, so for the C2H4 Cl2, similar way. So we have dC2H4 Cl2 divided by dt. Remember, we don't have the stream for the 1,2-dichloroethane, it's only product. So it means that it's only in the stream 3. So we have here NC2H4Cl2 at the stream 3 plus DC or DN, sorry. In here you write the N. Okay. Don't forget because it's number of mole. So you need to write the N here. So Dn C2H4Cl2 divided by dt. So this is for the reaction. Okay, so similar, yeah. So just make the one system for you, like this is perhaps reactor. You can use the system, it's like reactor, like this. So you have stream 1, 2, and 3. So it's more easy for you to calculate. Then we have another case, it's for the H2. This is a stoichiometric coefficient. So I believe that you know about the stoichiometric coefficient. For example, I have the reaction hydrogen with the oxygen and become the water. So here you have the coefficients is equal to 1. Here you have the 1 divided by 2 and in here is equal to 1. But to indicate that which one is the reactant, which one is the product, you can give the positive and negative. So when you have the hydrogen and then the oxygen, normally like for the reaction, we always give like the stoichiometric, like indicate positive here and then negative for the water. So we can calculate the sum of the, we can say that in here is stoichiometric coefficients with the I. So I in here is represents of any species I. So you can change, for example, hydrogen, nitrogens, or anything like for the products or the reactants, you can calculate by sigma I, Vi multiplied by I equal to be 0. And how about the other? We have here the new one, X. X, it means molar extent reaction. So if you know that molar extent reaction is defined like how much the number of mole left in your reactions during the reactions process. So you can calculate the molar extent reaction. It's from the number of mole, yeah, and I. You can use the specification here. This is, we call it the molar extent reaction. Like Ni, it represents of the number. In here I just write, so it's make you recall number of mole in the system, yeah, or any in the for the species, any kinds of the species. I just say of compound or species. Species is compound at any time. So we don't know the time, but it's for the number of the moles, and then Ni0, it means the initial or T equal to be 0 divided by Vi, stoichiometry. So here is Vi, stoichiometric coefficient. So Ni0, it's, I just say in here initial number. Initial, it means in the origin, like when T equal to be 0, this is initial number of mole. So you can calculate the extent of reaction or X based on these equations. Then how we calculate for some illustrations, you have the electrolytic decomposition of water from the hydrogen and then oxygen. So here we have the water, and then it's become hydrogen and then oxygen. So in this case, like we have the reaction, yeah. So you have the initially like only 3 mole of the water are present in the closed system. So then at the sum later found that 1.2 mole of the hydrogen and only 1.8 mole of the water are present. And it show that the molar extent of the reaction based on the hydrogen and the water are equal, and compute the number of mole of the oxygen in the system. So here, don't forget, write the reactions. And then you got to know that divine for the stoichiometric. So in here, like the product, yeah. So you have the reaction is the water. So here I can write Phi H2O equal to -1. And then here for the Phi H2, it's equal to the +1. Yeah, here is +1. And then Phi O2, it's equal to the +1 divided by 2. So then we would like to try to define this equation. So we can try to expand this equation. H2 plus half O2 become minus H2O. It should be equal to be 0. So we can calculate for the H data. If they ask, because in here they ask you about the molar extent of reaction, it means it's X, yeah, like we discussed before. The number of mole in the reaction minus of the initial number divided by the stoichiometric coefficients. So then we can calculate for the H2, everything have in here. So we can calculate the X equal to the 1.2, because here that it's given in the problem is 1.2 mole of the hydrogen. So 1.2 minus, how about the initial? Is it initial we have the hydrogen? We don't have hydrogen in initial. We only have water. Then we can minus 0 divided by stoichiometry of H2 is 1. So it means that we have positive 1.2 mole. So this is how we calculate the extent of molar extent of reaction. And how about the other? The other for the H2O data, for the H2O, because for the water, yeah. And then for the water, molar extent reaction, it means 1.8 minus 3 divided by 1, and minus 1. Because here, like the water, it was negative, and then plus, it's become 1.2 mole. Why is minus 3? Because in the problem given that it's 3 mole. So initially it means in the inlet, or you can say that in the start, initial it means originally in the start you have the water. It means like when the P is equal to B0 in the system, you already have the water, and then we want to earn the product. It was the X2 and then half oxygen. So then you can try to calculate the X2, and then for the H2O will be equal to the 1.2. Then for the B, because we want to calculate about the oxygen, so then we can have the NO2, yeah? And oxygen in here, remember, is only in the product, so we don't have the initially. So we can calculate Ni, use this equation, Ni0 plus Vi multiplied by X. So from where this equation, this is the coefficients for the total of the mole. Yeah, it's equal to the, normally it's equal to the initially plus the stoichiometric multiplied by extent of reaction. So you can substitute extent of reaction. It means Ni minus Ni0 divided by V. So it's equal to the Ni equal to the Ni0 plus Vi multiplied by X. So then we can calculate the V and NO2. So initially we don't have the oxygen, yeah, only the water, so we don't have. And then the stoichiometry of the oxygen plus 1 divided by 2 multiplied by 1.2. So here we got 0.6 mole. Okay, so I don't think it's difficult for you, right? Because the molar extent reactions you may have learned in the senior high school in the chemistry. However, perhaps like you don't have the relation yet with the how to calculate in the system. So then, in this case, we can calculate further. And remember that molar extent reaction is not fractional conversion. So it's different. For example, like if you reaction A plus B and become C is 100%, this is not fractional conversion. So the extent molar reaction, that's why they can be like 1.2. So you don't need to multiply 100. If you have reaction, only 80% reaction. So this is conversion. But for the molar extent reaction, they just try to indicate like how much the mole is left after the reactions, or you can see that for the number of the mole at the specialty minus the initial condition divided by stoichiometry. So it's not the fractional of the conversion. So it's not mandatory if you have the result, it's more than 1. But conversion is cannot. Conversion it should be 100. So you need to have more than 100. For the external reaction, you can have more than 100. It's no problem. But for conversion, cannot. You cannot have them more than 100. Okay, so then we can go to the rate of the change from the mass balance of the chemical reaction in the molar base. So I think this is the specified for if you have from the chemical reaction, we can write the dNi like the previous one, yeah? dNi divided by dt. This is for the reaction. This is equal to the Vi multiplied by X. So X, it means the molar extent reaction. Then we can try to divide that dNi divided by dt. It's equal to the sigma K is K equal to 1. So then you can divide Ni K, so here dot, plus Vi dx divided by dt. Then if you want to integral the form, it's T1 to T2. So then we can have the Ni at T2 minus Ni at T1, right? So here T1. And then here will be equal to the sigma K, and then K equal to 1. And then integral T1 to T2, and then you have Ni K dt, and then plus delta Ni reaction. Okay, so in this case, you may have that the sigma K equal to 1 up to K, and here we can write delta Ni K plus Vi delta X. So the extent molar reactions we can calculate by this way. How to calculate if you have the integrations T1 and T2. The similar, with this case, we have the illustrations of the 232. So you have the high temperature acetaldehyde, CH3CHO dissociate into the methane. So here you have acetaldehyde become methane and the carbon monoxide. So at the 520 degrees C, the rate at which acetaldehyde dissociates, and then they give you the specific equations, and where the C is concentration, and you have the vessel is 1 liter, and initial concentration of the acetaldehyde is 10 kilomole per meter cubic. So if you only have the 5 mole of acetaldehyde reacts, how much your methane and the carbon dioxide is produced, and develop the expression for the amounts of acetaldehyde, methane, and carbon monoxide present at any time, and determine how long it will take for the 5 mole to have the reactant. So we're going to solve this case. So then it means that you need to know like each of the species composition like we did before. Only here with the extant molar reactions, we can calculate based on the previous integral T2 minus T1. So try to start the solutions. I will recall how to calculate the concentration equal to the N divided by V. Remember, concentration mole per liter. Yeah, I believe that in chemistry you learn about this. Then for the C acetaldehyde, so you have 10 mole per liter. So it's mean equal to the 10 kilomole per meter cubic. So if you have initially C equal to the N per V, so we can calculate the N, yeah, because you know the V. In the problem give you the V is equal to the 1 liter vessel. So it means that N is equal to the C multiplied by V. Then in here we can write CH3CHO will be equal to 10 mole per liter multiplied by 1 liter. So neglect each other. So you will have the 10 mole. Then we can write for the NCH3CHO acetaldehyde is 10 minus X. So X in here is for the X10 molar reaction. So I write here X is molar X10 reaction. Okay, so here we have the NCH4 because NCH4 we don't know. Remember in the problem they just give you the 10 mole of the acetaldehyde, but you don't know about how much the methane and then how much the CO. So you just give the X symbol, molar X10 reaction as X, and then NCO as X2. Then you can determine for the A because they ask if you have 5 kilomole acetaldehyde and then how much the methane and then carbon monoxide. Then we can write here for the A and CH3CHO, for the T minus NCH3CHO, for the T is equal to be 0, you have 5 minus 10 mole. So it means you only have the minus 5 mole or minus X because you have the originally 10 and then only 5 mole is reacts. And then for the B parts, for the P, because they ask about develop the expression how much the acetaldehyde, methane, and carbon monoxide present at any time and how long it does it take. So we can try to divide the rate of change. So D and CH3CHO divided by dt will be equal to D and CH3CHO divided by dt in here reaction. So we can rewrite this V stoichiometry. Remember CH3CHO dx for the molar X10 reaction divided by dt. Or you can rewrite this equal to the minus because it's react, so minus of dt, reactant, yeah, is minus. Then how we divide these equations? So we can write here D N per V is equal to the concentration. So we can write like this, Ver divided by V and then divided by dt. Remember this one, it's equal to the C. CH3CHO, so the same. It's just only rewrite way and then to calculate the expression. It's more easily. Then the problem give you the expressions of the questions, yeah, minus 0.48. So we can write here minus 0.48 and then C power of 2 CH3 CH0 acetaldehyde. So here equal to minus 0.48 and then CH3 CH0 divided by V squared. So in this case, it's meter cubic per kilomole second. So we can try to express this equation with the, remember the previous, we have the NCH3CH0. It's for the 10 minus X, 10 minus X10 molar of reaction. So this one. And then we can substitute because in here we have the dx divided by dt. From the previous, we have the minus dx divided by dt. This is because of the for the NCH rule. So phi CH3 CHO dx dt. So we can substitute this and try to divide that dx divided by dt, it's equal to 0.48 10 minus x power of 2 divided by v. Yeah, so here the NCH3 CHO dt, right? And then you have the mole divided liter per scone, or you can 0.48 10 minus x power of 2 mole per scone. Then if you want to integral t equal to B0, integral, I can write more simple here. Integral t equal to B0. So it means that t equal to B0, your x is equal to B0, right? So in this case, you can have the t equal to B0 and t equal to t. So you can try to expand 1 divided 10 minus x t minus 1 divided 10. This is equal to 0.48. Or you can rewrite x t equal to 10 minus 1 divided 0.48 t plus 0.1 more. So this means that you have the xt for the CH3 CHO. You can calculate or you can substitute even for the calculation CH4 and then the CH for the CO, yeah, for the carbon monoxide and the methane. So you can use these equations to calculate the xt or the rate of change. So simplify, we can write the, sorry, we don't have a space, so I just write here, it's okay. So N CH3 CH0, it means this is at T, and then it's equal to the 1 divided 0.48 T plus 0.1. So this is if you would like to calculate, because it's 10 minus, this is for the acetaldehyde, and then for the CH4, because you have the 10 mole, the same case for the NCO, the same mole for the carbon monoxide and then the methane. So we can calculate 10 minus 1 divided 0.48 T plus 0.1. So this is for the NCH4 and then for the CH30. So this is the result for the acetaldehyde and this is the result for the methane and then the carbon monoxide. So xt in here is represents like if you have acetaldehyde, how much you can earn the CH4 and then C0. But for the acetaldehyde itself, it's equal to the 1 divided 0.48 T plus 0.1. So it's equal to the previous statement. Yeah, we have the when we integral the T equal to B0 and T equal to T, it means how much the acetaldehyde consumed that you can produce the methane and then the carbon monoxide. So I think today, thank you very much for learning together in chapter 2. We can continue for the chapter 3. Thank you so much for your attention. See you.